Today we are going to be doing an interactive webinar. So you will be as involved as I am. You will be responding uh, and acting into the giving your feedback to us all the time. So if you have any question, you can use the webinar platform to send it to us. So we will go straight into the Kahoot. I see some people have still not joined. I would suggest you join at the earliest. Let's give a minute and two, little bit more for everybody else to join. So we are planning to conduct this webinar in 4 parts. Today is the first session, and we want to get your feedback, comments, suggestions on improving our webinar so that it will be more effective. So let us start, and here is a simple quiz for you. We are going to be talking about ethylene for next 90 minutes. So what is the chemical formula of ethylene? Uh, I think it would be an excellent time to refresh our basics of organic chemistry that we all studied in high school. Uh, Ethylene is one of the important petrochemicals produced worldwide. It gained prominence especially after World War II. Before ethylene, acetylene used to be used as a base. Ethylene has no direct end uses and has been used exclusively as a building block in petrochemical industries. US refiners started separating it from the refinery waste gases and then later on started producing it from ethane, which was obtained from the byproducts. So uh, most of you got it right. The formula of ethylene is C2H4. It has 2 atoms of carbon and 4 atoms of hydrogen. The formula is C2H4. Thank you very much. Let's move on to the next question. So ethylene has carbon to carbon bonding between the 2 atoms. So I want to find out from you whether it is single bond, double bond, triple bond, or quad bond. Carbon is one of the few elements that can have long chains of its own. It can have single bond like alkanes, and some examples are ethane, propane. They are the feed for ethylene cracking. Well, very good. Most of you got it right. Carbon to carbon double bond compounds are known as ethylene and propylene. They are the desirable products. Carbon to carbon triple bond is known as alkynes, such as acetylene. Multiple bonds are generally a lot more stronger. Single bond has a dissociation energy of 90 kilocalories per mole, while double and triple bonds have dissociation energies of 174 and 230 kilocalories per mole. So let's move on. Let's summarize. Ethylene, the chemical formula is C2H4. Its technical name is actually ethene as per IUPAC. Molecular weight is 28.5. It's a colorless flammable gas with sweet musky odor. As I said, it's very reactive and combines with other chemicals easily. So it's a very important building block for the petrochemical industry. So let me start spend a little time on myself. I want to introduce you. If you don't know me, my name is Ashutosh Garg. I am a chemical engineer. I passed out of IIT Kanpur in 1974. Since 1976, I've been working on fired heaters and combustion systems. I have worked in KT India, Engineers India, and KTI Corporation in US. And I've been working at furnace improvements from 1996 onwards, revamping heaters and improving their performance for past 25 years. So we started furnace improvements in 1996 with a mission to improve the performance of existing fired heaters. Since then, we are focused on revamping fired heaters and increasing their capacity, run length, and efficiency. We have 3 patents on improving the performance of fired heaters. We have a contrarian approach, and we have been constantly challenging the conventional wisdom and worked on new approaches to solving problems. We have 3 offices and a team of 35 engineers and designers. We can take projects on turnkey basis. We are one of the few heater companies with its own CFD modeling office. I want to take this opportunity to thank all our customers for their business and support, and that is how we have made this webinar possible. I want to start thanking out by our New Delhi team of process engineers for working hard for the past 6 weeks. Our team of process, mechanical designers, and engineers have been working on putting this presentation together. Thanks to all the team members for their hard work. All material that has been presented here today is from literature, and no proprietary information has been disclosed in this presentation. I just want to make it clear that there is plenty of information available in literature, and that's what we have used today for our webinar. So we did this course with another company in 2017 on cracking heaters. But this time what we did was we asked all our participants to provide us 3 topics and concerns they would like to see covered in our webinar. I want to let you know we had a tremendous response, and almost 150 of you responded with the questions. And that gave us 300 topics to be covered. We want to cover what concerns you. So we have thrown out our old course material, and we will be covering your comments and topics in the next 3 sessions. We will also post replies to all your technical queries on our Facebook, LinkedIn, and website. Please keep us sending more questions at us, and we will try to answer them. So I want to talk a little bit about cracking furnaces or any fired heaters. They all have 2 sides. Cracking furnaces also have 2 sides. One is what is happening inside the tubes, the radiant tubes, and that is reaction kinetics, and that is a proprietary technology of 4 or 5 companies in the world. We cannot help you there. But the other side is the flue gas side or the fire side. And it is the fire side in all fired heaters which control the heat transfer. So we have a lot of experience in dealing with fire side issues, fire side problems, and we can help you with any and all fire side, whether it is concerning burners, whether it is concerning fan, burners, combustion, refractory. In fact, if you look at all the feedback what we have received, Majority of the feedback is concerning the fire side. You know, flame impingement, coil bowing, flashback, heat distribution, high tube metal temperatures, run length issues, tube failures. All these things are related to the fire side, and we would be able to help you with all these problems. In our experience, flame impingement is one of the most common problems in fire heaters, and we can definitely help you improve your burner's flames. Look at all these questions, and these are all feedback from what we have received from you, like low efficiency, NOx emissions, CO2 emissions, high shell temperature, hotspots, refractory failures, fans, burner tip clogging. All these issues are on the fire side. So we should be able to help you with all these issues, and as I said, the only thing what we don't do is the reaction kinetics inside the tube. So that's the thing we cannot do, but everything else we can help you. And you look at all these things, typical failures, flame patterns, you know all those things, we will try to help you with the operational issues, questions, your license. I want to make it very, very simple. We can help you with the draft if you are having draft limitations, if we can help you with the ceramic fiber, CO2 emissions, greenhouse gas emissions. If you want to reduce greenhouse gas emissions from your furnaces, you want to reduce NOx emissions from your furnaces, we can help you there. So we got tons and tons of questions actually. I don't know whether we can cover all these questions in the next 3 sessions, but we will try. And as I said, we will put them in the Facebook, LinkedIn website. Furnace operation and control, furnace startup, burner cleaning, CO2 emissions, draft calculations. Most of those things are concerning fire side, and we should be able to help you. Give us a chance to look at your furnaces and improve the performance. So again, let's get your feedback. What type of feedstock are you using in your cracking furnaces, whether you're using gas, liquid, or liquid and gas both. So all right, so majority of people are using gas, 42% of the people, 20% are using liquid and gas feedstocks. Some are using liquid only, 5% of the people are using liquid, 21% are using liquid and gas both. Now we do have some people, participants who don't have any cracking furnaces, so I just want to get feedback over here. Thank you for your feedback. Let's move on. What type of gaseous feedstock is used in your cracking furnace? There are choices of LPG, ethane, NGL, and propane. So these are the 4 typical feedstocks which are used in the cracking furnaces. Well, most of us are using ethane, and you will see because in US it is available in plenty, especially because of the shale gas revolution. And there are some people who are using LPG and NGL. Well, thanks for the response. If you are on the liquid side, what type of liquid feedstock is used in your ethylene cracking furnaces? The choices are naphtha, hydrocracking residue, gas oil, or other refinery heavy oil products. Well, majority of you are using naphtha. Naphtha is an important feedstock for cracking. Thank you again. So if you look at the feedstocks for the cracking furnaces, we are looking at gaseous feedstocks, which are basically ethane, propane, butane, LPG, and NGL is a mixture of ethane, propane, and butane, or the liquid, which is naphtha, gas oils, hydrocracking residue, other refinery heavy fuel oil products. Just want to let you know that there is a effort in the industry or trend in the industry to use crude and crack the crude straight and get into different products, including ethylene. So they are thinking of even cracking crude directly. So just to give you a feedback or information, you need 3 times naphtha as compared to ethane for the same ethylene production. So that's generally the thumb rule. So naphtha is a very important liquid feedstock for most of the cracking furnaces. It is a mixture of more than 100 hydrocarbons, boiling range in the range of 85 to 390 degree Fahrenheit. Uh, Typically, naphtha, which is ranging from 85 to 200, is called light naphtha. 200 to 390 is called heavy naphtha. So, and full range naphtha is between 85 to 390. Naphtha can be also analyzed because on the density, also based on the content of paraffin, isoalkanes, olefins, naphthenes, and aromatics. It's called piona analysis. So the feedstock has a potential for big range of products, what can be achieved. So this is a analysis of 2016 and 2021. World is using about 50-50 naphtha and ethane. The trend is more towards ethane in US and more towards naphtha in Asia and Europe. But even LPG is holding steady at about 14%, others are about 8%. Also, ethylene process is very energy intensive, and we generate 2 kg of carbon dioxide gas for each kg of ethylene produced. So that's another thing to take notice on. Well, here is a question for you. What is the total worldwide how much ethylene is produced every year? Ethylene is used in large variety of downstream sectors such as production of polyethylene, ethylene oxide, polyester, PVC, EDC, ethyl benzene. So, well, most of you got it right. It is almost touching 200 million tons per annum. So, Asia Pacific region has the largest ethylene production capacity now, and the worldwide production is continuously increasing. So, there are almost 315 ethylene plants throughout the whole world. And this is just an estimate. My estimate is about there are 3,000 ethylene cracking furnaces. There are 117 companies in 32 countries who are producing ethylene. The largest companies are BASF, Dow Chemicals, ExxonMobil, Lyondell, Ineos, Sabic, Formosa Plastics, DuPont, and approximate growth is about 5 to 6% per annum. You can see over here in 2005, we had a worldwide capacity of 107 million tons per annum. And now in 20 years, it will be almost 3 times, 283. I mean, right now it is about 2019, it was 192. So it's almost like 5 to 6% growth per annum. And so lot of growth in plastics. I mean, you can see plastics are entering every sphere of our life. So, and to make those plastics, we need these ethylene or polyethylene in our plant. So generally, plants will have a multiple of cracking furnaces, and that is because of variation in feed, variation in run length. I mean, and because of run length, you can have a different this thing. So just want to get a feedback as to how many furnaces are there in your plant. On an average, about 8 to 10 ethylene cracking furnaces are there. So we have a wide range actually. Anywhere you can see it's uniformly split. I mean 3 to 5 is there because and rest is almost evenly split. So we have the whole range of ethylene furnaces in our plants, chemical plants. So what is the production capacity of your ethylene cracking furnaces? So the production can be anywhere between 50,000 metric ton per annum to more than 150 or 200,000 tons per annum. If it's around 50,000, then it's a very old, small cracking furnace. And if it is 200,000, then it is a new high intensity cracking furnace. So most of the people have between 100 to 150 metric tons per annum ethylene capacity, which sounds right. Nobody has 50,000 metric tons per annum. These were the old furnaces which were built in, I think, around 1950s or maybe even earlier. And some have between 50 to 100,000 metric tons per annum. These could be small furnaces built in India, maybe around 1960s or 70s. So thank you again for your feedback. So we want to find out what is the final product from your ethylene plant, because ethylene, nobody produces ethylene. They are always producing something else. Ethyl benzene is a precursor to styrene. Polyvinyl chloride is a plastic. LAB is a detergent. So, and polyethylene is a plastic again. So lots and lots of products. So most of the people are producing polyethylene or PVC, surprising anyway, very good. We have a good response here. Thank you. So if you look at the ethylene, there are lots and lots of uses, starting with polyethylene, ethanol, ethylene oxide, vinyl acetate, 1,2-chlorodiethyl. Then you can make ethylene glycols, glycol ethers, ethoxylates. Vinyl chloride can go into polyvinyl chloride, engine coolers, polyesters. We haven't listed polystyrene here. We have not listed linear alkyl benzene. So lots and lots of uses are there for the ethylene, and it's growing worldwide. So our feedstock is gas, and our product is ethylene. So how do we get to that reaction? What happens? What is the process, or what is pyrolysis? Uh, well, almost everybody got it right. Pyrolysis is decomposition at high temperature. Uh, pyro means, it's a Greek word. Pyro means fire, and lysis means breaking or losing. So pyrolysis is breaking of molecules with heat. It is defined as thermal decomposition of organic materials at elevated temperatures in the absence of oxygen. It is also called thermal cracking. Uh, it's mostly done in the presence of steam. Dilution steam, although does not take any part in the chemical reaction, but it does help in improving the yield of ethylene by reducing partial pressure, as well as in coking. So it does help, I mean. So that is the basic pyrolysis, what is taking place inside the radiant coils where the reaction is taking place. So we want to see what are we feeding to our ethylene furnaces, or what temperature are we feeding the gas to or liquid to our ethylene cracking furnaces. We have 4 temperature ranges over here. Most of the feedstock, so it's ranging all over the place. Generally, you want to feed the coldest so that you can recover the most heat uh, from your furnaces or hot flue gases. Typical temperature is 100 to 250 degrees for the gas furnaces. People who are heating more than 400, maybe they are having vaporized naphtha entering into the system. So that's a very big range here. There is somebody who is feeding at less than 100 degrees. Thank you. Let's talk about the outlet temperature. What is the feed outlet temperature from the cracking furnaces? So pyrolysis reactions take place at high temperatures. So feed outlet temperature could be very high depending on the feedstock. Range is from 1400 to 1600 degrees F. Okay, so we have range all over the place, evenly split. Ones which are in the high temperature zones is like ethane cracking. I think the low is around naphtha cracking. So, but thank you again for the response. And you can see how much this is one of the hottest furnaces. I don't think we go to these temperatures of 1600 in any other furnaces. So very, very critical. And most of this high temperature has been possible because of advances in the metallurgy. By better alloys, we are able to get into uh, higher temperature zones. So metallurgy has really, really helped.